Welcome back, grade 12s and colleagues that are watching. I believe you had your water, you had your comfort break. So we're busy with organic reactions. So before the break, I outlined now how I go about trying to remember everything in an exam. So we created this analogy as well as how to remember the reaction conditions associated with heat as well. So the idea is, can we apply this now into an exam situation or an exam problem? So there's a question here that I have. So we'll try and see if we can be able to answer and apply what we just did. So before I can even go into the questions, the trend is we will be given a flow diagram. So a lot of information will be given from the flow diagram, and from the flow diagram I should be able to identify a few things. I will write another recipe that I work with. It's RCP. The R now is for the reactants. The C is for the condition. And then P is for the product. So there's an interlink between each one of them. So I just need two for me to be able to identify what type of a reaction it is, or what processes am I expected now to go with. So with this RCP, if I am given a reactant and a condition, then the examiner is going to assess the product. Can you see that? If I am given the product and the condition, it means now the examiner is going to ask the reactant. So it's always best for me now to have an interlink between the two. So I'm going to look at reaction 1. So when I look at reaction 1, what is it that I have? I have the reactant, and I won't say it's a condition, but it's some form of information that relates to the condition. Then I have the two. So what did they ask? I'm expecting for them to ask me something about the product, which will be R in this case. So when I look at the reaction R, I am given the product, the condition. So what is it that they are going to ask me? They are going to ask me something that relates to R, which will be a reactant for reaction 2. When I look at propan 1-ol reaction 3, what is it that I'm given? I am given now the reactant. So the questions that could follow is condition and product as well. So this is a way of me trying to be able to say, but this is the approach that I am going to have in conjunction with the analogies that we just developed. So when I look at this, I can automatically say for reaction 1, I am starting with a saturated hydrocarbon, 100%. So I'm starting with saturated hydrocarbon, saturated. Then do I move to unsaturated? No, I am not moving to unsaturated. But am I moving to saturated? Yes, I am moving to saturated. So it means now reaction 1 should be substitution. Easy from this. I don't even know the questions thereof. Then I am moving from R to propan 1-ol, but I am using now a dilute strong base. So I use now here my reaction conditions. If it's dilute, then it must be substitution. So reaction R also R2 also at substitution. So this is how easy it becomes when I have now outlined all the key pointers in this particular topic. So we'll try and answer questions and apply these methods that we are working with. So the very first one, it says write down the name of the type of the reaction that, okay, sorry, it's represented by reaction 1. So 4.1.1, we already said we are moving from now saturated to saturated, so it should be substitution. Very easy, substitution. (4.1.2), also we need to identify reaction 2. So I said the only way of identifying reaction 2, we are starting with a dilute sodium hydroxide. So dilute is associated with substitution. Then we move like that to say it must also be another substitution, of course. It must be another substitution. So easy marks. So we already have 2, and remember the idea is to get around 7 marks. So we have identified different types of reaction, substitution, and substitution, addition, as well as elimination. Then we further go on and say consider reaction R1 and R2. Write down the IUPAC name of compound R. The IUPAC name of compound R. So the IUPAC name, it means you must just substitute 1 hydrogen there because it's substitution. So we'll have 1, 4, 3. It will be something like 1 bromo, propane, 1 bromo, propane, and it's just 2 marks. So 1, 1, 2 marks. Then we further move on. Reaction 3 takes place in the presence of a catalyst and heat. That is now reaction C. Let's look at reaction 3. They say it takes place in the presence of a catalyst and heat. So where does it come from? It's now this part where they ask me about heat. So name of the catalyst. So we are starting from an alcohol. So probably it will be from saturated, and the heat is involved, so it has to do with elimination thereof. So what did we say about elimination? I must have concentrated acid. So concentrated acid, the name of the catalyst there should be 4.14, should be concentrated. Sulfuric acid, name of formula, sulfuric acid. Then it will be just 1 mark. Keyword, concentrated sulfuric acid. Very, very important. It's elimination under heat and catalyst. So concentrated works for elimination. Then we further move on, give now the IUPAC name of compound T. The IUPAC name of compound T is ethanoic acid. Yes. Compound T is ethanoic acid, because the idea there is formation of an ester thereof. Remember, ester is part of elimination, where we remove now water. Then the structural formula of U is an ester, so the first thing that we look for will be 4.15 will be, okay, 4.5, it's ethanoic acid. Okay, let's start there. Ethanoic acid, obviously from reading the stem, ethanoic acid, and then 4.16, the structural formula is us now having the correct functional group thereof. So it is an ester, so we will have C, 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 and then we'll have another C here. So this will be propyl ethanoate, propyl ethanoate. And then the way we mark it is to ensure that you have now the correct functional group and the whole structure is incorrect. You see what I did here? Because I quickly rushed, so it means I was going to lose now this mark for hydrogen here. So kindly ensure that each and every carbon has a maximum now of 4 bonds. I could have now lost that 1 mark for the hydrogen. So it's very, very key for us to be able to say, let's look into the structures being fully correct. Then after this crash course, we can go now to rates of reactions. So for rates of reactions, we go back, it's around 19 marks. So we'll also design a crash course for that, such that we revise and prepare you accordingly. But remember, everything goes with practice and giving yourself more time. But before we can go into that, the idea here with rates of reactions also is we need to know which factors affects rate of reaction and how they contribute to that. So we'll start with the pillars again. We have now these factors that affects rate of reaction, and it is always best to know how each one of them influences the rate of the reaction. So we'll start by saying we have the first one, which is concentration. We have surface area. We have temperature. And then we have a catalyst. So these are the factors. So we are going to design a way of saying how best can I go about using the collision theory in each one of them. Because with collision theory, we say particles must collide with sufficient kinetic energy in the correct orientation. So with that being said, I will say here, but now if I am changing concentration, what is it that I am changing? Basically, I am changing the number of particles per unit volume. Number of particles per unit volume. This is key. And when I apply now the collision theory, it's something that I am going to focus more on. But when I have a surface area, so I can easily say The larger the surface area, larger surface area, more particles are exposed to effective collisions. So this will be my bullet number 1 when I am trying now to answer the questions that follow. When I look at temperature, I should be able to say increase in temperature increases the overall kinetic energy of particles. Then with a catalyst, what it does is it lowers the activation energy by providing an alternative pathway. Lower the activation energy by providing an alternative pathway. So once this is into place, it becomes easy for me to develop a strategy of how to answer the questions. Because every question that says now use the collision theory to explain how a catalyst or how temperature influences rate of reaction, it will be easy because I exactly know how each and every one of these influences the rate of reaction. So my bullet number 1 will necessarily be based on that. Other questions that will follow will be just questions to test my knowledge, but the key idea here is how best can I apply the collision theory. Even if I am given the graphs, even if I have a certain way the examiner is trying to assess, it will be easy for me as long as I understand how collision theory is applied. So I am going to have bullet number 1 and bullet number 2. So at bullet number 2, we say molecules or more molecules. Let's write it in that sense to say more molecules will have a greater kinetic energy than activation energy. That is now bullet number 2. Bullet number 3, I am looking now at saying more or less effective collisions per unit time. Finally, I must conclude to say the rate of reaction increases or decreases. So I can say rate of reaction increases or even decreases. So it becomes an easy way of me now just choosing which one is relevant. But the first thing is I must be able to understand, did we have an increase in temperature? If yes, then bullet number 1 will be increase in temperature increases the overall kinetic energy of particles. Thereafter, more molecules will have a greater kinetic energy than activation energy. Then more effective collisions per unit time. So it becomes just an issue of comparing. So if I have more effective collisions per unit time, the rate of the reaction increases. If now I'm comparing a surface area, it means now the one with a larger surface area, it means I have more particles that are exposed for effective collisions. That will be my bullet number 1. Then the rest will be the same. So if I am asked about a catalyst, then I should say there at bullet number 1, a catalyst provides an alternative pathway by providing, by lowering the activation energy. Then that should be my bullet number 1. So this is the sequence that we are trying to emphasize, especially when we are asked now to apply the collision theory. So when we apply the collision theory, it's always best for us to use these bulletins that we have. So this is the sequence of us trying to get the correct answers. Then we can look into the questions that follow. So the questions that follow is at question 5. They say here, study the Maxwell-Boltzmann distribution curve for a certain reaction below. Then they say P and Q are labels on the axis. What quantity is represented by P and Q? Before we get into that, remember we are also looking at the achievables. So in this topic of rates and of reactions, it's plus minus 19 marks. So we are looking at achieving around 9 marks. So the 9 marks should somehow be easy to collect, in a sense that when I look at P and Q, it is just Maxwell distribution curve. So Maxwell distribution curve, it works with the number of particles under the curve. So where there is R, it is the number of particles, sorry, for Q, it is the number of particles. P is the number of particles with kinetic energy, and then R will be our activation energy. Because now R here represents the minimum energy required for the reaction to take place. So it will be easy for me to say at P we have now a kinetic energy of particles. Kinetic energy. Then at Q we have the number of particles. So this should be number of particles. So I'm on my way of trying to get the maximum marks, of which in this case should be 9 marks. So I should be able to get a 1 there and a 1 there. Line R represents the minimum energy required for the reaction to take place. Write down the term for the underlined weight. All of us must be able to get it right. That is now the activation energy. Activation energy. Then nice 1 mark. How will the shaded area be affected when a catalyst is added? Remember, what did we say about a catalyst? A catalyst is a substance that now lowers the activation energy by providing an alternative pathway. So it means now the energy will now start to increase the number of particles, because now the R will shift to the left. So the correct answer here should be increase. So I've already got my 1, 2, 3, 4 on my way to 8 marks or 9 marks. So 5.3 is very clear to say use the collision theory to explain how a catalyst influences the rate of reaction. Then I come back to this thought process that I came up with to say, but they are asking me of a catalyst, so I must be able at bullet 1 to say a catalyst is a substance that now increases the rate of reaction without undergoing any permanent change by lowering the activation energy by providing the alternative pathway. Then I will have more molecules that have greater kinetic energy than activation energy. Then more effective collisions per unit time, and the rate of the reaction increases. So that is the 4 marks that the examiner is looking for. So if I am happy with how I answer in terms of bullets, then everything should be in place, because when you look at it, it says to me, this 4 marks, it's easy to get, provided you know how best to apply what? To apply the collision theory. Because it says here also, as part of the achievables, explain in terms of the collision theory how various factors affect the rate of the reaction. So that is exactly what we have done. And as part of the achievables as well, interpret Maxwell-Boltzmann curve, the number of particles against kinetic energy. Explain the effect of catalyst, temperature, and concentration on the rate of reaction when using Maxwell-Boltzmann distribution curve. So this achievables is what was assessed from 5.1 to 5.3. So it shouldn't be much of a complex problems. It shouldn't be much of us not getting the correct marks, because it is now what? Part of the achievables. It's things that when I sit down and prepare for my exam, the best thing to look for is ensuring that each and every bullet that is here, I am able to perform or answer them according to what is expected. So most people will say, but now this section has calculations. Yes, it does, but the calculations thereof will be more of your stoichiometric calculations. So I'm just going to show you how to go about this stoichiometric calculations. They will differ with time and the type of question that is being assessed. But generally, once we have a balanced chemical equation, we have a graph, we have some information that is given, it becomes very easy for us to work with stoichiometric calculation. So I'm going to try and give you a process that you can use when dealing with stoichiometric calculations. It will be for rates of reactions, it will be for acids and base, anything that has to do with stoichiometric calculations. This will be the approach to follow, because the idea is we are moving from the known to the unknown and the link thereof. So let's start by saying I need now to have the number of moles. Let's say the moles of A in this instance. So what is it that is going to help me or assist in terms of me getting the number of moles of A? There are many equations that I can use. The first one will be N is equals to M over M. Thereafter, I can use C is equals to N over V. Then I can use N is equals to N over NA. I can even further move on and say I can use N is equals to V over Vm, depending on which information is given to me. If I am given the volume, automatically I will be now using the Vm. If I have the volume and the concentration, then I can use C is equals to N over V. If I have the number of particles and the Avogadro constant that is given, I can easily now calculate the number of moles. So if I have mass that is given, it's easy for me to calculate the number of moles. So the number of moles will be our starting point of everything that we are going to go to. Thereafter, we link now this now will be the given. Let me say this one will be the given. Some information should be given in order to assist you in getting the number of moles. So once this is given, we say we need now molar ratio. So the molar ratio is now from where? From the balanced chemical equation. Balanced chemical equation, 100%. From the balanced chemical equation. What does molar ratio do? Now we have now a link between the given and the unknown. So for me to link what is asked as well as the information that is given, I am going to use my molar ratio. So the molar ratio is the one that I use now from the balanced chemical equation in order to link between the given and the unknown. Then I can be able now to say I will get the number of moles now of B. But what can I do with the number of moles of B? I can go back to calculating the mass, calculating the concentration or the volume, calculating now the number of particles, as well as now the volume thereof. It becomes easy because if I am asked for the mass, it means I can easily take it now to percentage purity. If I am asked for the concentration, I can easily now take it to pH is equals to log the concentration of hydronium ions. So it becomes somehow nice and easy because the link thereof is very, very clear. So somehow I need an information that will give me the number of moles. So once I have this information, I must use the molar ratio. From the molar ratio, use any of this. If I want percentage purity, then it means I must get the mass. If I have the mass, then everything will somehow be clear. Can I apply this? Yes, let me look into the information that is given here at 5.43. They say now the calcium carbonate in 6 grams of impure sample reacts completely with 0.03 mole decimeter cubed of HCl in 26 minutes. But we are given a graph there of the average rate of production of carbon dioxide and the initial concentration of HCl. So what is it that I have here? I have the concentration of HCl, and then the reaction took about 26 minutes to complete, but the average rate was 50 centimeter cubed per minute. So what does this say to me? It says before I can calculate anything here, it's important for me to calculate the rate and get the volume that was produced. So use the information in the graph to calculate the percentage purity of calcium carbonate. Assume that the molar volume of a gas at 25 degrees, it is now 24,000 centimeter cubed. So it's very clear to say they want me now to calculate percentage purity of calcium carbonate. So percentage purity will be now what? Will be percentage purity is equals to mass over the total mass of the sample. Total mass of a sample multiply by 100. Sorry, multiply by 100. So whatever I do, it says eventually at the end of it all, I must calculate now for that particular mass, because the mass of the sample is given. I already have the 6. So it means whatever I do, the idea thereafter is for me to eventually get the mass. So what can I do? I can use the rate of the equation for rate. We'll do it quickly. Rate is equals to, in this case, we have changing volume of carbon dioxide that is being produced, changing volume over changing time, because remember rate is a measure of time, but we are told that the average rate is 50 centimeter cubed per minute. So we'll substitute our 50. Then V here will be now what? It took 26 minutes, so we'll have our 26 minutes, and then I will have my changing V as something like 13300 centimeter cubed. Now somebody will ask, but why this? Is because I am looking at this particular information of mine. I do not have the mass for me to get the number of moles. I have the concentration, yes, but the volume is not given of what was produced, and we are looking only at HCl. The volume that is given is the molar gas volume. It's not this volume here. Do I have the number of particles? No, I don't have. So the reason why I went for that is because the molar volume of a gas is given. So if I have this particular volume, then I can use volume of the molar volume of a gas. From the molar volume of a gas, I can easily calculate the number of moles. After calculating the number of moles, then I can follow this particular procedure. Hence I'm saying this will be now the crux of stoichiometric calculation. So when you look at this, it says, but the information that is given somehow should link in a way that I'm able to calculate my number of moles. So I could not calculate the number of moles using this one, and this one, but because I am given now the molar volume of a gas from the information that is given here, I am able now to convert my rate into the volume that I need. So once I have that, it's easy to say from now the formula N of carbon dioxide is equals to V over Vm. Then the volume that was produced, 1,300 divided by 24,000. Then I will get my number of moles of carbon dioxide, which is something like 0,0542 mole. Then I look into my balanced chemical equation. I look at my balanced chemical equation between what? Between carbon dioxide and calcium carbonate. So the ratio is 1:1. So I can easily say the number of moles of calcium carbonate is equals to the number of moles of carbon dioxide. Therefore, 0,0542 it's the number of moles of calcium carbonate. So I have addressed this part here of the number of moles of calcium carbonate. So now that I have this number of moles, what is the question? Percentage purity. So if the question is percentage purity, it means I must calculate the mass. So what must I do? I will say N of calcium carbonate is equals to now the molar mass divided by mass, mass divided by molar mass. So we want the mass, so it will be 0,0542, and then we want the mass. The molar mass will be something like 100. Then I will get my mass as 5,42 grams. But I did not answer the question, but I did say earlier on that from grade 10 and grade 11, I know that once I want to calculate percentage purity, my mass should be divided by the total mass multiplied by 100. So the mass that I have here is 5,42 multiplied by 100, and then the percentage thereof is 90,33%. So this is how you go about the stoichiometric calculations. So this is a way of me saying once it is a stoichiometric calculation, once there's a balanced chemical equation, the key idea there will be try by all means to ensure that you follow this guideline there. The guideline will assist you a lot in terms of the approach. It will assist you a lot when you are dealing with acids and bases as well, chemical equilibrium, stoichiometry. It's part of paper 2 from question 2 to the last question. So you need now to be able to look into that. And remember, we have other topics that are also important: chemical equilibrium, acids and base, electrolytic cell, galvanic cell, of which they will be part of the exam. So the key thing that I want you to go and look into is majority of schools now are finishing off the curricula. So to save yourself time, kindly follow us on YouTube, because the majority of topics that are left, there are videos there that will guide you and assist you. Unfortunately, because of time, we have to end few things, and the idea is we cannot be able to do everything. But the little that we have done today, kindly watch the video once more, download the video for you, in order that you are going to use it again and again to address the misconceptions and the common errors that you are doing. So as you prepare, kindly check other videos that speaks to rates of reactions, speaks to chemical equilibrium. I remember there's about 6 parts of acids and bases that I did. That is where now I explained everything in detail. We did few exam type of questions. That is the reason why I'm saying today now the video will end here, because others will be just a reference of everything that we completed before. So from me, thank you very much for watching and being with me throughout the day, and all the best for examinations that are coming. Remember, the only way for you to achieve is to prepare in time, to avoid panics, and to avoid you stressing towards the examination. So let's prepare, let's chew the bread piece by piece, and then eventually we'll eat the whole bread. Thank you very much and have a lovely day. Thank you.